Chem 161. I'd like to take a look at some Chapter 3 material, specifically chemical nomenclature. So how do you name substances? Now, before we get into naming the different types of substances that are out there, specifically the different types of compounds, let's talk about what types of compounds there are, so it makes a little more sense when it comes time to name them. This is Chapter 3 material in Tro's textbook, so let's take a closer look. You can see this fancy looking tree diagram. Now, the way we're going to classify the substances is by their particle type. There are different ways to classify substances. You can put them in categories of solids, liquids, and gases. That's one way. In this classification scheme, it's by particle type. So the two main types of substances really are the elements and the compounds. Now, we're not dealing with mixtures, okay? There are lots of different mixtures out there, okay? We just want to talk about single pure substances, so they can either be an element or a combination of elements. You remember, compounds are what you have when, let's zoom in a little closer. Compounds are what you have when two or more elements are combined in there we go. Two or more elements combined together in fixed proportions. And this means that there are two or more types of atoms in a compound. Okay, this is opposed to mixtures. Mixtures, the proportions can vary. Like if you have sugar water, you might have 10% of this stuff is sugar and 90% of it is water, but those proportions can vary. Maybe it's 20% sugar and 80% water. Okay, variable proportions. Compounds are always fixed proportions. Okay, for instance, if you're talking about the substance water, 11% of it is hydrogen and 89% of it is oxygen. Those proportions are fixed. Okay, no matter where your water comes from, it's always 11% hydrogen, 89% oxygen by mass. Fixed proportions. Okay, we'll talk about compounds here in just a bit. Suppose we have a single element that we're focusing on. Now, we're classifying substances by their smallest particle type. Okay, so elements can either be atomic, molecular, and there's also this third category called covalent network. We know that each element has its own unique type of atom, and so if we're talking about a single element, then the substance must have only one type of atom. So let's see what these categories are. Now, the atomic elements examples are helium gas, gold solid, and liquid mercury. So take any one of these. Suppose liquid mercury. Now, the particles of this liquid substance, they all look alike, and being a liquid, they're all close together. So let's take a closer look at one of these particles, a representative particle. Inside this particle, there's one atom of mercury. And these particles are not directly connected to each other. They're just close together. So each particle is separate, and inside the particle is one atom. So the smallest particle of liquid mercury is a single atom of mercury. Okay? And that's why we represent it as Hg, and you could put the 1 there, but if there's just one, you don't have to. So Hg, liquid. Now, solid gold would also be atomic, and if you were to examine a piece of gold, look at all of its particles, they all look identical. Pick out any one, and there's just a single atom of gold in there. Okay, also an atomic element. Molecular elements examples are H2, N2, O2, F2, Cl2, Br2, I2. So there's 7 of those, and then there's a few more. Let's talk about maybe one of these. Chlorine, for example. Okay, here's chlorine. Chlorine gas. Now the reason the formula is Cl2 in parentheses gas, well, let's see. You need to keep your gas inside of a container, and all of the particles of the chlorine gas, they of course look identical. That's the thing about having a single pure substance. All of the particles are identical. So pick out one in particular, and inside that particle you'll see 2 atoms of chlorine that are actually connected together. And the connection here is called a covalent bond. It's a sharing of a pair of electrons. So what happens is this chlorine atom on the left has an electron that it likes to share, and so does the chlorine atom on the right. And so what happens is the electrons, one from this one and one from that one, they link up. Electrons like to pair up, and when they pair up, both of the chlorines are holding on to that pair. So this chlorine is holding on to the pair, and so is that chlorine. It's holding on to the pair. And since they're holding on to the same pair of electrons, they are in fact linked. And that's called the covalent bond. It's a sharing of an electron pair. So this is a molecule. A molecule is when 2 or more atoms are connected by covalent bonds. So the smallest particle of chlorine gas is a 2-atom molecule, and that's why the formula is Cl2. There are several of these other diatomic molecular elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So when you find these substances out there in nature, they come in the form of 2-atom molecules. So they're diatomic molecules. Iodine is a diatomic molecular solid. Bromine is a diatomic molecular liquid. Chlorine, fluorine, oxygen, nitrogen, and hydrogen are all diatomic molecular gases. Notice that there are 7 of these diatomic molecular elements, and on the periodic table you'll find most of them right next to each other in the shape of a 7. So there are 7 of them, and they are arranged in the shape of a 7 on the periodic table. So we call that the rule of 7s. There are a few other molecular elements worth noting. Sulfur comes in the form of S8 molecules. So if you find some sulfur out in nature somewhere, maybe next to a volcano, find some yellow sulfur crystal on the ground, take a piece of crystal, examine it in the lab, look at all of the particles, and they all look alike. So any one particular particle, look at it closely, and you'll see inside that one sulfur particle there are 8 sulfur atoms connected together in the shape of a ring, actually, and they're all covalently bonded together. Okay, so these ring-shaped molecules are the smallest particles of sulfur crystal, and that's why the formula is S8 solid. Phosphorus comes as P4 molecules, selenium comes as Se8 molecules. Now what happens if you take one of these molecules, like maybe this chlorine molecule, and you break it in half? It's pretty easy to break a molecule in half. Well, the 2 separate atoms would be unstable, and eventually they would reattach. So this is the stable form of chlorine, not monatomic chlorine. Monatomic chlorine would be single chlorine atoms that are floating around. Okay, they're unstable. Chlorine likes to come as Cl2 molecules. So those are the molecular elements. All right, so there are several of them, and it's best if you just learn these. Now, there's a third category of elements, and that's called the covalent network. And an example of that is the diamond form of carbon. If you examine a diamond, so get yourself a nice big fat diamond and look at all of the particles. They're all carbon atoms, and what you would actually see if you could see this with chemical instrumentation is that all carbon atoms in the entire diamond are covalently bound to each other. So it's like one gigantic molecule. You know, all of the carbon atoms are bonded to each other through covalent bonds. In fact, if you look at any one carbon atom, it's covalently bonded to 4 other atoms. Okay, each carbon atom is bonded to 4 other atoms within the diamond structure. So that is a covalent network. Okay, now the 2 main categories of elements are the atomic and the molecular elements, but be aware that there are covalent network elements out there like diamond. Compounds are divided into 2 main categories here. You have the molecular compounds and the ionic compounds, and then there is also a third kind of smaller category called the covalent network category. Molecular compounds, examples include water, liquid water, propane gas, solid sucrose, and molecular compounds are the particles or molecules. So let's take a closer look at water, liquid water. It's made of particles. All of these particles look the same. So look at any one of them in particular, and what you would see inside this particle are 2 hydrogen atoms covalently bonded to an oxygen atom in the middle. Now, this oxygen has to covalently attach to both hydrogens at the same time. So that means the oxygen has to have 2 electrons that it contributes. It has to have 2 available for bonding. So 1 to pair up with this hydrogen's electron as a covalent bond, and then another electron from the oxygen to pair up with this hydrogen's electron as another covalent bond. So there are 2 covalent bonds attached to the oxygen, and later on in this course we'll talk about the shape of this molecule. It's actually like a V, a triangular shaped molecule. So this is the smallest particle of water. You cannot cut this particle any further and still call it water. So the smallest particle of water has 2 H's and a single O, and that's why the formula is H2O. All right. The other examples in here, like solid sucrose, its molecules each contain 6 carbons, 12 hydrogens, and 6 oxygens. So a molecule of sucrose is quite a bit bigger than a molecule of water. Okay, all of these atoms are somehow covalently attached, and the sucrose molecule has an interesting shape. The glucose molecule, this is glucose sugar, it has an interesting shape. It involves a ring as well, and then stuff coming off the rings, and we'll look at that shape later on near the end of the course. So molecular compounds, these are also called covalent compounds. They're made of molecules. Their particles are molecules. Ionic compounds consist of ions. So you can tell when you have an ionic compound because it's pretty much always going to be a metal and a non-metal, like sodium chloride or magnesium iodide. So you have these metals over here along with non-metals. Now, ionic compounds are made of ions. The metals, like sodium and magnesium and potassium, they tend to form positive ions, and the non-metals tend to form negative ions. Okay? Now, if you have a positive ion, there has to be a negative ion nearby. Okay? So what happens when you form an ionic compound is the metals, being positive, are missing an electron. So let's take a closer look at, say, sodium chloride. You see a sodium atom has 11 protons and 11 electrons. Let's find that on the periodic table. Let's see. Let me find this periodic table and then I'll show it to you. Okay, here we go. So sodium is element number 11 there on the periodic table. So a sodium atom has 11 protons and 11 electrons. But sodium tends to form +1 ions. Being in column 1A, okay, that's telling you it likes to form +1 ions. So it loses an electron in order to have the same number of electrons as neon. That's what, you know, elements do. They lose or gain electrons in order to achieve the same number of electrons as these noble gases. So sodium, you know, it loses one, and now it only has 10 electrons to be like neon. All right, so sodium likes to form a +1 ion. Now, if sodium loses an electron, it has to go somewhere, and you can see chloride nearby has gained an electron. This is a negative ion. So sodium is a positive ion and chloride is a negative ion. Okay, so these are opposite charged ions. And what a sodium chloride structure looks like is you have a negative ion, a positive ion, negative ion, a positive ion, negative ion, and that's what an ionic compound structure looks like. It's basically opposite charged ions, you know, in a big three-dimensional structure. And if you look at any one of these sodium ions, it's surrounded by chloride anions. And if you look at one of these chloride anions, it's surrounded by sodium cations. So you see, electrons are not being shared between nearby cations and anions. The electron has been transferred completely. Sodium is missing in its electron, and chloride has it. So it's this separation of oppositely charged ions that is holding this whole structure together. This is called an ionic bond. Okay, it's a transfer of electrons as opposed to a covalent bond, which is a sharing of electrons. So ionic compounds are made of ions. Magnesium and iodine are also form an ionic compound, but the magnesium is a +2 ion, and therefore it needs 2 of these minus charged iodides. You see, magnesium is a +2 ion. If we find that on the periodic table, you see magnesium is in the +2 column, 12 electrons, and so by losing 2, it would have 10 electrons like neon. That's why magnesium forms a +2 ion. Iodine is 53 electrons, so it needs to gain 1 to be like the noble gas xenon. So that's why iodine forms a -1 ion. And so you need 2 minus charged iodines to balance the +2 charged magnesium, and that's why the formula is MgI2. So ionic compounds, normally a metal and a non-metal. Now, just like there were a couple of main categories and then an extra category called the Covalent Network for the elements, we also have that category for the compounds. An example is silicon dioxide. This is a quartz crystal, and silicon dioxide, also called quartz, is like a big gigantic molecule where all of the silicon and oxygen atoms are connected. In fact, if you look at any one silicon, it's connected to 4 different oxygens through covalent bonds. Okay, so the whole thing is like a giant molecule, and so it should be distinguished from molecular compounds, in which is a bunch of tiny molecules all separate from one another. Okay, covalent network, giant molecule. Okay, so very good. That's how to classify your pure substances. Let's take another look at that whole diagram right there, and let me clear it up for you. Okay. Now, how do you name these substances? So that's our next topic. Well, when you're talking about elements, it's much easier to name the elements. In fact, if the element is in its normal form under standard conditions, then the name of the element is simply the element name. So for instance, hydrogen gas comes in the form of H2 molecules. So if that's the substance you're dealing with, you simply call this hydrogen gas. Gold, the normal form of gold is the atomic form. So gold solid, you would call this solid gold. This one would be called oxygen gas because O2 is the normal form of oxygen. But suppose you find yourself some oxygen gas in which the particles are single atoms, not O2 molecules. Normally, we find oxygen as O2 molecules, but consider this substance. This is not a normal form of oxygen under standard conditions. This is a different allotrope, okay? An allotrope is another form that you can find the element in sometimes. Not the normal form, it's another form, an alternative form. Okay, so oxygen has several allotropes. This is the normal one, but there is monatomic oxygen, and when you're dealing with another allotrope, you have to give it a special name. So we would call this monatomic oxygen gas because we're dealing with a single atom. Now, just like there's monatomic oxygen gas, O3 is called triatomic oxygen gas. That's another allotrope of oxygen. And this is also known as ozone, O3 molecules. Okay. Sulfur, the normal form of sulfur is S8. So we would just call this sulfur crystal or solid sulfur, whatever. Solid sulfur, sulfur crystal. Crystal is solid. So either one of these works. We don't have to indicate that there are 8 atoms of sulfur because that's the normal form. A couple of others. Carbon has several important allotropes. Now, it's common to just say what allotrope of carbon you're talking about. Normally, if you have solid carbon, you're usually talking about graphite, okay? But it's still common practice to just indicate the allotrope of carbon. Okay, so carbon solid graphite, this is carbon graphite. Carbon solid diamond, this is carbon diamond. C60, that's an interesting allotrope, and that's called carbon buckyball solid. Okay, so carbon, just common practice to indicate the allotrope, no matter even if you're dealing with the normal form or not. Okay, so those are elements. It's simply the element name unless it's a different allotrope. Then you have to indicate the allotrope. Right. So next, let's get into compounds, and there's a lot more for compounds here. So the naming scheme for compounds depends on the compound type. Let me clear this up a little bit. It depends on the compound type. Molecular compounds. Now, we can break molecular compounds into different categories. Okay, remember there's multiple ways of categorizing matter. So suppose we're just talking about molecular compounds. One way to categorize molecular compounds are organic molecular compounds and inorganic molecular compounds. Organic molecular compounds are carbon-based compounds, and we don't really cover those much in general chemistry courses. We'll talk about them from time to time in this course, but we're not going to talk about how to name all of the organic molecular compounds out there. That's covered in OChem, or organic chemistry. Okay, so we're not going to name them. The inorganic molecular compounds, these are the compounds that are not carbon-based, and there are a couple of categories that we're going to go through. Acids, and a couple of subcategories of acids, binary acids and oxyacids, and then all other molecular compounds. So inorganic molecular compounds will cover the acids and the other ones. Okay. The ionic compounds, let's do first. Ionic compounds are named by naming the cation first, the plus charged ion, and then the anion second. So that's how you name an ionic compound. You have to know the name of the cation, and then you have to know the name of the anion. And it's the cation name, anion name. Now, the cations, you remember we're typically talking about metals. So when we say cation, anion, this is usually metal, non-metal. So the cations, many of the metals form predictable charges. And for those cations, the name of the cation is simply the element name. The other metals that form variable charge, the way we name those cations is we say the element's name and then we follow that by the charge. So there is an alternate naming scheme for these variable charged ionic metal cations. So let's take a look at the textbook figure 2.13 or figure 3.7. Either of these two figures show us the predictable charge formed by many of the metal ions. Let me find this and then I'll point you to it. Okay, so this is in chapter 3. Let's have a look at figure 3.7. So figure 3.7, this is 3.5. So 3.5 tells you, the molecular elements. Let's go to 3.7. Okay, here you go. Here you go. So these are the metals with invariant charge. Now, you can remember which metals always form a +1 charged ion because they're in the first column. In fact, we're looking at column 1A. So that's where you want to use this naming scheme for the columns. Columns 1A, those metals always form +1 ions. So sodium +1, potassium +1, rubidium +1. They're always +1 ions. If I say that you have a sodium ion, it's a +1 ion. Now column 2A, these metals form +2 ions. So if I say you have a strontium ion, it's a +2 ion always. Now columns 3A form +3 ions. Okay, like aluminum. If I say you have an aluminum ion, it's a +3 ion. All right. Now let's find that other figure. Actually, I want to find you the other figure as well. So that figure 2.13, because that shows you the nonmetals. I thought it showed you the metals, but let's take a look. Okay. So 1 second, I'll get that to you. So this is figure 2.13. So here's chapter 2, and let's go to 2.13. This is figure 2.11, 2.12, 2.13. Here we go. This is maybe a little more clear. Okay, so you see this is the +1 column, the +2 column, the +3 column. Now, the nonmetals typically form negative ions, and this is your -1 column, your -2 column, and your -3 column. Okay? So that's how you can remember which one you're talking about. What's wrong with my... Oh, what happened here? Where'd it go? Here we go. Okay, so +1, +2, +3, -1, -2, -3. Now, if you're dealing with a transition metal, something in this region, well, they have different charges. Like iron is right here, and sometimes it's a +2 iron, and sometimes it's a +3 iron. So those are the variable charge ions, the transition metals. Okay? Now, let's go back to our document CHEM. So for example, sodium plus, the name of this ion is simply the element name, because sodium is in the +1 column. Right there is sodium right there. It's always a +1 ion. So the name of this we call sodium. Mg +2, this is called magnesium. Simply the element name, because magnesium is in the +2 column right there. Okay. Gold +3 charge. Here we have to indicate the charge in parentheses. So the name of this ion is the element's name, and in parentheses the Roman numeral 3 to indicate that it's a +3 gold ion that we're talking about. And that's because you know, gold is down here somewhere. Where's that other periodic table? So there is gold right here, element 79. Gold forms different charged ions. Sometimes it's a gold +1, sometimes it's a gold +3. So if I say you have a gold ion, you don't know which ion I'm talking about. So I have to tell you, it's a gold 3. Okay, we're talking about a gold +3. So that's why we indicate the name in Roman numerals, because it's one of those variable, you know, charged ions. So iron is right here. Sometimes it's iron +2, sometimes it's iron +3. I would have to tell you which type I'm talking about. All right. Now, here's a few more examples. Calcium +2. This is simply the element name. We don't need Roman numerals, and that's because calcium is always a +2. It's in the +2 column. So you remember this, these are always +1s, these are always +2s. So the calcium 2+ ion is simply called calcium. And the next one is cobalt with a +1 charge. Here I have to indicate the charge in parentheses, and that's because cobalt is in the variable charge section right there. Element 27, sometimes there are cobalt +1s, sometimes there are cobalt +2s. So the exact one needs to be indicated. You see there's the cobalt +2. This is the difference, right? This one's called cobalt 1, this one's called cobalt 2. Now we'll talk about polyatomic cations shortly. Okay, those are like groups of atoms that have a positive charge associated with it. Okay, these are monatomic cations. So one atom with a single charge, you know, monatomic cations. Okay, now I should mention that there's also an older naming scheme that we can see in table 3.3 for some of those variable charged atoms. So let's look at table 3.3. Where is this at? Okay, so here we go, table 3.3. Some of those metals that form different types of charges, like chromium +2, chromium +3, they're usually, you know, if there are two main ions the one with the lesser charge gets the us ending, and the one with a greater charge gets the ic ending. So several of these with two main ions, we can distinguish them by the us and the ic. So the +2 chromium is chromous, that's the older way to name it, and the +3 ion is chromic. And iron comes as two main different ions. These are the only two that you'll really see. The +2 is called ferrous, and the +3 is called ferric. So if somebody says they're dealing with the ferric ion, you know that it's a +3 iron. Okay, so the iron +3 can be named as iron 3 or ferric. All right, and there's several other examples in this table. So we'll reference these from time to time. It's good to be aware of this other older naming scheme. Okay. Let's go back. Okay, so those are the cations. We'll deal with the polyatomic ones after a little while. Now the anions, the way you name anions, the monatomic anions, so a single atom with a charge, is very simple. Okay, it gets the ide, so you get the base name of the element, plus the ide suffix. So for instance, the Cl- ion is called chloride. The S-2 ion is called sulfide. The O-2 ion is called oxide. The N-3 ion is called nitride. So it's always ide. This is bromide. This is iodide. Okay? And you can check if you want to make sure that these are predictable charge ions. This is in fact in the -1 column. So is that, and so is that. Sulfur and oxygen are in the -2 column, and nitrogen is in the -3 column. So these are the normal charges that you see on these anions. We'll talk about polyatomic anions shortly. So very simple to name monatomic anions. Right. And here are several examples of compounds. So you can identify these as ionic compounds, remember, because you have a metal. Metals pretty much always come first, too. You have a metal and the nonmetal. So this is the metal sodium, and that's the nonmetal iodine. And the name of this is sodium iodide. Sodium is a +1 ion, but it's always a +1 ion because it's one of those predictable metals. Okay? So this is simply the element name, and then the nonmetal gets the ide. So sodium iodide. Down here, K2O, this is also ionic. You have a metal and nonmetal. You have two potassiums to balance the oxygen, and that's because if you go back, potassium is right here. It's one of these predictable ones right there. Okay, it's in the +1 column, so you need two of these +1s to balance the oxygen, which is in the -2 column. So let's go back to that other one. Remember, oxygen is in the -2 column. So two pluses balance the -2. Right, so you have to have two positives and two negatives. So that's why the formula is K2O. So two +1s balance the -2 oxygen. And so since this is a predictable charged metal, we simply give it the element name potassium oxide. Okay? Now, likewise, you should be able to take a name and turn it into a formula. I know that oxygen always forms a -2 charge, and potassium always forms a +1 charge. See, this is a -2 charge, and that's a +1 charge. Okay? When you have a metal and non-metal, we're talking about an ionic compound. So if I see this name, This is a -2 charge, and that's a +1 charge. So I must need 2 of these guys to balance one of those, and the formula would be K2O. So given the name, you should be able to identify the formula, or given the formula, identify the name. MgS, this is magnesium sulfide. Magnesium is always a +2 ion, and sulfur is always a -2 ion. So you remember the full element name, and this one gets the "ide" suffix. So again, magnesium is right there in the +2 column, sulfur is in the -2 column. So they balance each other out. You just need one of each, right? One of each, that's a formula. And so the name is the element name, and then the "ide." Okay, magnesium sulfide. This right here, strontium, is a predictable ion, and so is nitrogen, of course. The nonmetals always are. So the name of this is strontium nitride. Now, if you wanted to make sure this formula makes sense, strontium is a +2 ion. All right, let's check that. Strontium is right here. It's in the +2 column, and nitrogen is in the -3 column, right there. So you have 3 positive 2s, that's a total of +6, which balances 2 -3 is a total of -6. So yes, they do balance. Okay, and since this is a predictable metal, it's strontium nitride. Here, aluminum phosphide. This is a +3, and that's a -3. This is in the +3 column, and that's in the -3 column. Predictable, so we don't need Roman numerals. Okay, this one right here, Al2O3, aluminum oxide. All right, each aluminum is a +3 charge, so you have 2 of them. That's a total of +6, and each oxygen is a -2 charge, so you have 3 of them. That's a total of -6. So it balances again. Aluminum oxide. Now, when you're dealing with elements that have variable charge, you need to indicate the charge in parentheses. So AuCl, this is gold, and that's chlorine. What's the charge on the gold here? Well, gold is one of those elements. Gold is one of those elements. Let's find it. There you go. That forms variable charge. So we're not sure what the charge on the gold is right away, but I know that chlorine is in the -1 column. Right? See there, right there. Chlorine is a -1. So that means the gold must be a +1, because one of these balances one of those, and if this is -1, then that has to be +1. So the name of this is gold 1 chloride. You have to indicate the charge in parentheses here, because this is one of the transition metals. Okay, their charges are indicated in parentheses with a couple of exceptions, but most part you have transition metal, charge is indicated in parentheses. So gold is right there, it's transition metal. Okay, this one right here, cobalt, and it is balanced by 2 chlorines. We know each chlorine is a -1 charged, so the cobalt is a +2 charge, because one of these balances 2 of those. So 2 negatives balance a +2. So this is called cobalt 2 chloride. And I should use the older name as well. If we go back to that older naming scheme, let's see, right here, you see cobalt +2, cobalt +3. This is the +2 is also called cobaltus. So we could also label this as cobaltus chloride, and that would tell us we're talking about the +2 charge cobalt. All right. This one right here, the next one, AuI3. What's the charge on the gold this time? Well, it's balanced by 3 minus charged iodines. Okay, so that's a total of -3. So that must be a +3. So this is gold 3 iodide. Okay, you remember the nonmetals always get the "ide" suffix. The metals need the charge if they're one of those transition metals, and gold is definitely a transition metal, so it needs the charge indicated. Manganese 2 oxide. I know that oxygen is a -2, and you have one of these, so one manganese means the charge must be +2. Okay? Manganese 2 oxide. Manganese is a transition metal. So manganese is right there. Element 25. It's a transition metal. You need to indicate the charge. And I don't believe there is an older naming scheme for manganese, so I don't see it on the list. So no older way to name that. All right. So yeah. Okay. And then right here, Fe2O3. Now, what's the charge on the iron? Let's look at the other guy. You have 3 -2 charged oxygens. Oxygen's always -2. So you have 3 of them. That's a total of -6. So that must be balanced by +6. And 2 irons means each one is a +3. So you have 2 +3s for a total of +6. So that's how we figure out the charge on the iron. This is -6, so that metals must be +6. And if you have 2 of them, each one is +3. Okay, so that's iron 3 oxide. Okay, and the iron 3 ion in the older scheme is called ferric. So ferric oxide. Right here, copper and bromine. We know that bromine is a -1 charged ion, and you have 2 of those, so that's a total of -2. It must balance +2. So that +2 is all on one copper ion. So that's a copper 2+ to balance the -2. So that's a copper 2 bromide. And using the older scheme, this is the higher charge. Okay, cupric bromide. Copper comes as +1 ions and +2 ions for the most part. So the larger one is the ic, cupric bromide. Okay, how about this? FeF2. This is iron, and that's fluorine. Fluorine is in the -1 column, so you have 2 of these. That's a total of -2. That must balance +2. Okay, so the whole +2 is on this iron. This is iron 2 fluoride. And this is the smaller of the common iron ions, so we would call this in the older scheme ferrous fluoride. Okay, so some interesting examples there. If you're able to follow along and this makes sense, then you're doing really well. Now let's have a look at some polyatomic ions. Okay, and I want to show you a table for the more common polyatomic ions. What a polyatomic ion is it's a group of covalently bonded atoms with a charge. It's kind of like a charged molecule. So imagine an entire molecule, all the atoms are covalently bound, and the whole thing has a charge associated with it. Okay, so that's a polyatomic ion. So let's look at table 3.4. Where is this at? This is coming up now. Here we go. Coming up next. And here are some common polyatomic ions. Acetate, this is the formula for acetate, C2H3O2. So this group of atoms has a -1 charge associated with it. Carbonate is CO3 with a -2 charge associated. And by the way, I don't think it matters if you put 2- or -2. Personally, I do it -2. Textbooks typically do it 2-. Okay, but I've seen both ways in textbooks, so I like the -2. Tro likes 2-. So this is called the carbonate ion. Hydrogen carbonate or bicarbonate is what you get when you add a hydrogen to the carbonate. and the charge on that is only -1. Okay, so this is bicarbonate or hydrogen carbonate. Hydroxide is OH minus. We'll see this one a lot. Nitrite is NO2 minus. Nitrate, NO3 minus. So you can have a look through the list right here. The only polyatomic cation is NH4+, or the only one in this list. There are others, but the only one that we're going to see this semester is probably the ammonium ion. Okay, so ammonium is NH4+. So here's phosphate, hydrogen phosphate, and dihydrogen phosphate. Okay, a couple of other important ones right here. Sulfate is commonly seen. This is sulfite. Okay, bisulfite or hydrogen sulfite. Peroxide is also an interesting one. You got 2 oxygen atoms with a total of -2. Cyanide. Okay, so you should learn the common polyatomic ions, and some of these we'll see quite often. All right. Now, when you are dealing with the polyatomic ion in your ionic compound, the name of the ion is simply whatever name you see here. Okay. So here are some examples. So Na, NO3, this is the sodium, and this is the nitrate. Sodium is a +1 ion, and nitrate is a -1 ion, right? Sodium is a predictable metal, so we don't need Roman numeral 1. It's just the element name, sodium. And then NO3 minus, this is nitrate. So sodium nitrate. Right here, let's look a little closer. So this is potassium, and that's the carbonate. So you should recognize the carbonate, a CO3. So let's show you that again. This is the carbonate right there. So this is a -2 charge on the carbonate, and that's why, or that's how it balances the 2 potassiums, because the potassiums are always +1. So you need 2 of these to balance the -2 carbonate. So this is simply called potassium carbonate. This is calcium. Calcium is always a +2 charged ion, and if you have 3 of them, that's a total of +6. So that has to balance -6. The charge is always balanced, and if you have +6, then that balances -6. Okay, the -6 is distributed over 2 of these guys. So each one must be -3. So PO4 -3. Let's look for that. PO4 -3. And that is right there, phosphate. PO4 -3. So this is called the phosphate. And so this is +6, -6. So this is called calcium phosphate, right? The metal, simply the element name, because this is a predictable charge metal, and then phosphate. Now you can look at the rest of them in this list. Okay, a couple more. Right here, this is potassium chlorite, and this is potassium chlorate. Okay, chlorite is different than chlorate. The potassiums are always +1s, but chlorite is Cl2 minus, and chlorate is ClO2 minus, and the chlorate is ClO3 minus. Okay, don't get chlorite and chlorate confused. You'll see, both of them from time to time. Okay, chlorite, chlorate. And also, there's also another one, hypochlorite. Okay, so there are several, and one more, perchlorate. So look at all these involving chlorine and oxygen. Okay, lots of polyatomic ions for chlorine and oxygen. And notice the naming scheme. hypochlorite, chlorite, chlorate, and perchlorate. You'll see this similar naming scheme for other elements. So there is such an ion as hypobromite, bromite, bromate, and perbromate. So there's also corresponding ions for bromine. So notice that most of these anions involve oxygen. And so these are polyatomic ions, but we also call these oxyanions because they involve oxygen, most of them. So a lot of them are oxyanions. And again, nitrite, nitrate. Okay. So sulfite, sulfate has one more oxygen. So anyway, right down here. How about we'll move down. NH4I. This is the one time where it's an ionic compound and it's not a metal. So this is the ammonium ion, the NH4 plus ion. We call this ammonium and iodide, the I minus. Okay, ammonium iodide. This one right here. This is the sulfite. That's an SO3 minus 2 charge ion. That's called sulfite. Here it is right here, the sulfite ion. And so that must balance a +2. So the lead has a charge of +2. And we would call this lead 2 sulfite. Lead 2 is also called plumbus, one of those older naming schemes. So see if the rest of these make sense to you. And if there is an older naming scheme, it's useful to say that name as well. Okay. Now, there is a systematic procedure for learning many of these oxyanions. Remember the ones involving chlorine, okay? ClO minus, ClO2 minus, ClO3 minus, ClO4 minus, and they're called hypochlorite, chlorite, chlorate, and perchlorate. Okay, iodine has its own set of oxyanions. So notice that the charges are always the same, but the oxygen changes. So as you get more and more oxygen, the charge stays the same. And notice that these are very similar to the way those are named. The one with the least amount of oxygen is called hypoiodite, and the one with the most amount of oxygen is called periodate. Okay? So, sulfur has its own set of oxyanions. Here the charges are always -2. And the one with the least amount of oxygen is hyposulfite. The one with the most amount of oxygen is persulfate. Okay? Phosphorus has its own set of oxyanions. Okay? Least amount of oxygen, hypophosphite. Most amount of oxygens, perphosphate. In the same kind of scheme. Hypoite, ite, ate, perate is always what you'll see. Hypoite, ite, ate, perate are the prefix and suffix that you'll always see, going from least amount of oxygen to most. So I want you to focus on chlorate, iodate, phosphate, and sulfate. Notice how chlorate and iodate both have 3 oxygens. Okay? Now, if you just memorize the formula for chlorate and iodate, you can figure out the formulas for the other ones. You know that per iodate, you just give it 1 more oxygen. Iodite, 1 less oxygen, and hypoiodite, 2 less oxygens. Same thing for chlorate. That's ClO3 minus. 1 more oxygen is perchlorate. 1 less chlorite, 2 less hypochlorite. So if you just memorize the formulas for the 8s, then you can figure out the rest of them. And you might think that the 8s always have 3 oxygens, but that's not the case. Sulfate and phosphate have 4. Okay, but again, if we just memorize these, then we can figure out the other ones. All right. It turns out that the 8s, sometimes have 3 oxygens and sometimes have 4, and there's an easy way to know which ones have 3 and which ones have 4. So here's a little periodic table that shows you the formulas for the corresponding 8s. Borate is BO3 minus 3 oxygens. Carbonate, CO3 minus 2. Silicate, SiO3 minus 2. All of these have 3 oxygens. Nitrate, NO3 minus 1, so 3 oxygens still. In fact, if it's any of these, it's also 3 oxygens. Iodate is IO3 minus. Bromate is BRO3 minus. Chlorate is ClO3 minus. Elements that are inside here, 4 oxygens makes the 8. So phosphate is PO4 minus 3. Arsenate is ASO4 minus 3. Okay, and these guys also have 4. So do you see the pattern? If it's inside here, this looks kind of like a 4, doesn't it? Starting with phosphorus, it looks kind of like a 4. If it's inside here, 4 oxygens makes the 8. Outside the 4, 3 oxygens makes the 8. And once you know how much the 8 has, knowing the other ones is very simple. And look at the charges. This is the minus column. All of these 8s have a minus charge. All of these have a minus 2 charge. These have a minus 3 charge, except for nitrate. That's an exception. Then minus 2, minus 3. So the pattern is for the 8s, 3 oxygens outside here, and then 4 oxygens inside here. And the charges are minus 1, minus 2, minus 3, except for nitrate, which is minus 1, and then minus 2, minus 3. All right? So maybe that'll help you, learn the 8s. And once you know the 8s for any particular oxyanion, changing the number of oxygens should be a straightforward, thing you can just know at that point. Okay. So a few more. Compounds right here. Let's okay. AlPO2. Now this looks like definitely an ionic compound because you have metal and non-metal. Aluminum is a +3 charged ion always. So the name of that is aluminum. And so this must be a PO2 minus 3. And what is this? Phosphate, phosphite, hypophosphite? Well, I know that phosphate is PO4 minus 3. So phosphite must have 1 less oxygen, PO3, same charge, minus 3. And hypophosphite must be 1 less oxygen than that, PO2 minus 3. So this is hypophosphite, PO2 with a minus 3 charge to balance the aluminum plus 3 charge. So this is aluminum hypophosphite. Okay. How about this one right here, the gold, and this looks like an oxyanion, right? So you have gold, you have this guy. What's going on here? Well, what is that? Bromate, bromide, hypobromite, perbromate? Which one of these? Well, bromine lies outside the 4. So 3 oxygens is bromate. And the charges again are minus 1, minus 2, minus 3, except for nitrogen, minus 3, or minus 1, and then minus 2, minus 3. Okay, so this is bromate, which is 3 oxygens with a minus 1 charge. Okay, so that's bromate. And since it's minus 1 charge, but you have 3 bromates, that's a total of -3. That balances +3. There's only 1 gold atom here, and so that +3 is all on that single atom. Okay, so that's a +3 ion. So it's gold 3 bromate. Okay, gold 3 bromate. So kind of tough, but if you learn the procedure, it is straightforward. Okay, a couple of these. How about this one right here? This is cobalt, and that's phosphorus something. What is it? Phosphate. Well, remember, phosphorus is outside the 4. I'm sorry, inside the 4. So 4 oxygens is phosphate. And the charge is the charge is -3. Phosphate is PO4 -3. So this one is, where is it? PO5. So that's per phosphate. And the charge on per phosphate is -3. You have 2 of them, so that's a total of -6. So that balances +6. So each of those 3 cobalts has a +2. So that's cobalt 2 per phosphate. And cobalt is one of those ones that can have the older naming scheme. So we should name this a cobaltus, right? Per phosphate. Cobaltus per phosphate. I forgot to include that in here. So using the older naming scheme. Now have a look at the rest of them. And this one right here is copper 2 hyposulfite. Copper 2 hyposulfite. Again, looking at sulfur. Sulfur is inside the 4. 4 oxygens makes sulfate. So the charge on sulfate is SO4 -2. So sulfite would be SO3 -2, and hyposulfite would be SO2 -2. SO2 -2 is hyposulfite, and this is in fact SO2 with a -2 charge. So that's hyposulfite, and it balances a +2 charge on the copper. Okay? So copper has a +2 charge, so this is called copper 2 hyposulfite. And copper 2 ion is also called cupric. So it's cupric hyposulfite as well. Sometimes you will see ionic compounds with waters attached. So let me show you a little bit about what I'm talking about. These are called hydrated ionic compounds, or hydrates. And these contain a specific number of water molecules per formula unit. Now, think of a hydrate as you have a salt, which is your ionic compound, but there's also water in there, okay? And this water, it doesn't mean the compound is wet. It's still a solid normally, but it just has water in the material, okay? And this water can be driven off if you heat up your ionic compound, and then you'll be left with the anhydrous, just the ionic compound alone without the water. So for instance, calcium chloride, you can find calcium chloride, each formula unit has 2 waters attached, and so we call this calcium chloride dihydrate. That's how you name this. Calcium chloride dihydrate. Calcium is a +2 charge. It balances the 2 minus chlorides, and there are 2 waters, so that's di, meaning 2 hydrates. And what this structure might look like is, okay, the calcium 2 pluses, here are the red ones. For each calcium +2, you have 2 of these chloride minuses. Okay? Now this formula unit, there are 2 water molecules attached. So the water molecules are these green spheres, these green circles. So for each of these formula units, so here's one formula unit, a calcium 2+ and 2 chlorides. And for each formula unit, there are 2 water molecules associated with it somewhere. Okay? So again, calcium, chloride, and then 2 waters. Calcium with 2 chlorides and 2 waters. So each formula unit has 2 waters associated with it. So the structure of the material, looks something like that. Ionic compounds, it's always, the structure always is like you have your cation and then your anions, and then your cation and your anions. It's kind of like alternating, charge, positive, negative, positive, negative, positive, negative. Okay, but when it's a hydrate, there's also water in there, distributed. So for each formula unit here, there are 2 waters. This is a dihydrate. Now, there are other prefixes. If there is only half of a water attached per formula unit, or that's really like 1 water attached per 2 formula units, then that's a hemihydrate. If there's 1 water molecule per formula unit, that's monohydrate. Then 2 is dihydrate, and there are other prefixes for more. So let's take a quick look at figure 3.9. So figure 3.9, here is an example of the cobalt 2 chloride hexahydrate. So this is the hydrate, it's a red solid, and if we heat this up, we would drive the water off to be left with the anhydrous form. So you see the structure can have different physical properties, if it's the hydrate or if it's the anhydrate. All right. So let's look at the last 3. Okay. So this is an ionic compound with a hydrate. So this is magnesium, and this is sulfate with 7 waters. So magnesium sulfate heptahydrate. This is also Epsom salt that you'll find in the drugstores. Okay. And then right here, this is cobalt. That's the cobalt 2 ion. Cobalt is one of those variable charged metals, so you have to indicate the charge. So this is the cobalt plus 2, and this is the phosphate minus 3, of course. And so that's a total of plus 6 to balance minus 6, so it does balance. So the name of this is cobalt 2 phosphate, and then octahydrate. Okay, and the last one, here's iridium, and here's bromine. Bromine has a minus 1 charge, so you have 3 of them, total minus 3, must balance the positive 3. So this is iridium 3 bromide with 4 waters tetrahydrate. Oh, this cobalt one has the older naming scheme, so this could also be cobaltous phosphate octahydrate. We add that cobaltous phosphate octahydrate. Okay, now we're getting there. So let's move on finally to molecular compounds. Okay, so molecular compounds. And I'll remind you, molecular compounds, there are organic and inorganic molecular compounds, and we're not doing organic. That's covered in OCHEM. Okay, for the inorganic molecular compounds, we'll divide those into the acids and all others. Okay, let's do the acids last. So the other ones, these are molecular compounds. And molecular compounds, there are no ions, okay? So we need prefixes here to indicate how many atoms we're talking about. Okay, we need prefixes. So let me give you an example. N2O, the name of this is Dinitrogen Monoxide. There are 2 nitrogens, 1 oxygen. Now, the naming scheme, the first element, which is nitrogen, you get the full element name along with its prefix. So dinitrogen, the whole name. But the last element, it gets the "ide" suffix. So it's not mono-oxygen, it's monooxide. So dinitrogen, the full name with the prefix, monooxide. The "ide" with the prefix. Okay, so dinitrogen monoxide. How about this one? P4S10. So we need the prefixes for 4 and 10. And here they are. 1 is mono, 2 is di, tri, tetra, penta, hexa, hepta, octa, nona, deca. So tetra and deca are 4 and 10. Okay, so this is tetraphosphorus, decasulfide. This one, you might think it would be called monosulfur hexachloride, 1 sulfur, 6 chlorines. Okay, but when there's only one of the first nonmetal, you can drop the mono prefix. Just normal procedure. Okay, so you don't have to, but it's what everybody does. So let's do it. This is monosulfur hexachloride. And this is not monocarbon monoxide, it's simply carbon monoxide. This one is dihydrogen monoxide. Okay, nitrogen trichloride. Now look at the last one, nitrogen trichloride. Wouldn't this be aluminum trichloride? What's going on there? How come this says aluminum chloride? But this one you need the tri. This is an ionic compound, guys. Alright, that's why I colored it red. So I was hoping to, you know, not throw you off, but, you know, maybe raise a red flag or something. Okay, so aluminum is a metal, and this is a nonmetal. Aluminum is a +3 charged metal, always, and chloride is a -1 charged nonmetal, always. Okay, so you see, we don't need prefixes when we're talking about ionic compounds, because aluminum is always going to be a +3, chlorine is always a -1, and if I know the charges, I can figure out the formula. If this is always a +3 and that's always a -1, I know that I need 3 chlorides to balance the aluminum. But I can't do that over here. Okay, if I just give the name like a nitrogen chloride, I don't know how many nitrogens and how many chlorines are in the formula, because I don't have charges to guide me. I need to indicate the number of each atom. Have 1 nitrogen, 3 chlorines. Okay, that's the formula. But you see, I didn't need any help down here. I have the charges to guide me. This is a -1 charge, that's a +3 charge, so I need 3 of these and 1 of those. Right? So molecular compounds, you need prefixes. Ionic compounds, you don't. Now, the last topic is the acids. So acids are discussed a lot in chemistry, and we're going to start talking about them here in Chapter 3. These are discussed further in Chapters 4 and 16. So we'll talk about chemical reactions involved in Chapter 4. Then we get to Chapter 16, go into acids in depth. So acids are molecular compounds, but they're interesting because they release H+ ions when dissolved in water. You can think of an acid as a molecular compound outside of water, but when you dissolve it in water, it becomes ionic. Okay? Acids have a sour taste, and some of them dissolve certain metals. Okay? So acids can be kind of corrosive. Okay, not all metals. It's very difficult to dissolve gold, but iron and other metals, they can be pretty easily dissolved in acids. Okay, sour taste and dissolve certain metals. They have other interesting chemical properties as well. And you remember, what an acid is it's something that releases H+ ions in water. So for instance, HCl gas. Okay, HCl gas. Now, using the naming scheme we just learned, this is a molecular compound because I see nonmetals. Hydrogen and chlorine are nonmetals. And I should call this hydrogen monochloride. Okay, hydrogen monochloride is the name that we should call this substance because it's a molecular compound. It turns out that the common name is hydrogen chloride. There's only one compound that forms between hydrogen and chlorine, and this is it. So it turns out that we don't really need the mono prefix. Even technically, it ought to have it. No one uses it. It's simply hydrogen chloride because there's only one compound that forms between H and Cl. All right, molecular compound, and this is a gas. And if you were to examine this this gas right here, you would see the particles are all very far apart from one another. They're in gas phase. Okay, they're all identical looking too. So if you examine one, you'll see a hydrogen and a chlorine atom covalently bonded together, sharing electrons. This is a molecule, the smallest particle of HCl gas. All you have to do is add a little bit of water to this stuff. So open up the hatch, pour in some water, then something happens. It turns into an acid. When you add it to water, now this is called hydrochloric acid, and the formula is HCl and in parentheses AQ, meaning it's an aqueous solution or dissolved in water. Okay, this is different. And if you examine this, it's no longer made of molecules. Those molecules have ionized. The H pluses have been released, and the Cl minus ions are left. So remember, the molecules, the two electrons were shared between the two atoms right here, sharing an electron pair. When it ionizes, the electrons go all the way over to the chlorine, okay, leaving that negatively charged, and the proton is then swimming around in solution separately as well. So these ions become separated from one another in water. So there's a bunch of water between the ions, and that's what happens. It ionizes in water, and that's what an acid is. It's something that ionizes in water, and the cation is always an H+. Okay? You can't just say an acid is something that ionizes in water. No, the cation always has to be an H+. That's what makes it an acid. Molecular compounds that release H+ when dissolved in water. So, now many compounds that contain hydrogen, many molecular compounds that contain hydrogen are in fact acids. Not all of them, but many containing hydrogen are acidic. And we'll talk more about acids later, but let's talk about how to name them quickly, and then that'll be the end of this video. So, a couple categories of acids. Binary acids contain hydrogen ions. We call those protons, right? So hydrogen ions and one other non-metal element, anion. So why do you call the hydrogen ions protons? Well, because hydrogen is a proton and an electron, and when you lose the electron, that's simply a proton that's left. Okay? So we're just talking about two elements here, the hydrogen and the nonmetal. So right here, you have HCl aqueous. So we know we're talking about the acid. So this is the acid. This is a binary acid, two elements. And the way you name this is simple. Hydrochloric acid. Okay? So binary acids get the hydro prefix and the ic suffix. So hydrochloric acid. And hydrochloric acid, remember, when it dissolves in water, it gives you H+ and the chloride. Okay? Now, this is a different acid. Okay, HBr. Well, we'll forget about the aqueous on all these. Okay, so this is HBr, and this is called hydrobromic acid. So you see the similar naming scheme. You get the hydro prefix and the ic suffix, hydrobromic acid. And this yields H+ and the bromide. How about this? Hydrofluoric acid. hydroiodic acid. Okay, H2S. Now, you need 2 protons to balance this one, because when this dissolves in water, this is, by the way, hydrosulfuric acid, the same naming scheme, hydrosulfuric acid. But when this dissolves in water, you get 2 protons and then that -2 sulfide ion. All right? Hydrosulfuric acid. Now, oxyacids are what you have when an oxyanion has a hydrogen attached. So, for instance, HClO3, this is called chloric acid. Okay, now the way you name this, you notice how it doesn't get a hydro. Okay, you never see this hydro anywhere for any of these oxyacids. So when the anion, okay, just look at these anions here. You have to ask yourself, what is the anion? That's what makes an acid different from another acid, is what anion, you get. All of them give you H pluses, but the way the acids are different are by the identity of the anion that it releases. Okay, so these release oxyanions, and this one releases the chlorate. Okay, the next one, HClO2, is chlorous acid, releases the chlorite. And the way you name oxyacids is you look at the anion that's being released. If it ends in ate, you turn that into an ic. So this is chlorate ion, so this is called chloric acid. This is the chlorite ion that it releases, so this is called chlorous acid. So ite gets turned into us, and ate gets turned into ic. This is chlorate, the chloric acid. This is chlorite, chlorous acid. Now this would release the hypochlorite. So this is called hypochlorous acid. This one would release the perbromate ion, so this is perbromic acid. All right. This one releases nitrates, this is called nitric acid. Again, ate goes to ic, ite goes to us. This one releases the sulfate. This is another acid where you get 2 protons per formula unit, and so you can call this a diprotic acid if you want. It's triprotic acids as well, but this one releases the sulfate, so 8 turns to ic. This is called sulfuric acid. This one releases phosphate, okay, PO4 minus 3, and that's why you need 3 protons. This is phosphoric acid. Okay, a couple more. This one releases acetate. So this is called acetic acid. That's what you find in vinegar, right? How about this one? H3PO2. That releases the hypophosphite ion, and it's called hypophosphorous acid. And finally, this one releases the dichromate ion, the Cr2O7 ion. It's called dichromate, so it's called dichromic acid. And that, folks, is nomenclature. So, a lot of stuff in this video. Probably a good idea to, browse through it again. Maybe at least look at the slides. Okay? So, I will see you guys next time. Aloha.